Hello everyone. I am an AI engineer from G-Hype, and my name is Hype. Today, I want to share with you APM32F4 flash simulating EEPROM. It will be divided into 5 parts. First, I will briefly introduce the difference between flash and EEPROM, and then introduce the principle of flash simulating EEPROM. Then I will introduce the difficulty in APM32F4 simulating EEPROM and the implementation of its code. Finally, I will explain another scheme of using flash to simulate EEPROM. Flash is flash memory. It is divided into NAND flash and NOR flash according to the storage unit circuits. Because the address line and data line are separated, NOR flash can be read and written in bytes, and they are mainly used to store or run the codes. They use the internal flash, which is a type of NOR flash. However, regardless of the type of flash, an erase operation must be performed before writing. Flash can only write data from 1 to 0. EEPROM is an electrically erasable programmable memory, and also a non-volatile memory. EEPROM can read and write in bytes, and does not need to perform an operation of erasing data before writing. You can see on the right, the picture lists some simple comparison items between flash and EEPROM. You can take a look at it. First is the interface. The flash inside the MCU does not have an interface, and the EEPROM has common interfaces such as I2C or SPI. In erasing, flash must erase before writing data, while EEPROM does not need to erase. In capacity, the capacity of flash is large, while the capacity of EEPROM is generally small, not more than 1 megabyte bit. In storage time, the storage time of flash is short, ranging between 10 and 20 years. However, the storage time of EEPROM is more than 100 years. In the number of reading and writing times, the flash is about 100,000 times, and its lifespan is limited, while the number of reading and writing times of EEPROM is large, about 1 million times. The read and write rate of flash is relatively faster. Because it is inside the MCU and has no external interface, the MCU can directly address, and the read and write rate is very fast. However, the read and write rate of EEPROM is slower. Please note that the flash introduced here is an internal flash of MCU. Next, I will introduce the principle of flash simulating EEPROM. We have already learned that before writing, flash must perform an erase operation, and the erase of flash is generally erase of a sector or page, and the smallest erase unit is sector or page. So, even if you are writing a byte, you need to first erase the entire sector, and then write. So the data volume of their operation is different. When we use flash to simulate EEPROM, a key point is that our experience of implementing reading and writing flash is consistent with that of EEPROM. The main key points are, first, users do not need to perform an erase operation when reading and writing flash. Then we can read and write by byte, and we should pay attention to it when erasing. But we cannot change the data already stored in flash, because even if we write a byte, it will erase the entire chip. Therefore, if you do not save the existing data first, it may erase the existing data. And when we write data, we don't need to perform byte-aligned operation. We can also consider a read and write across flash sectors. Then, the lifespan of flash should also be considered. That is to say, if the data has already been erased, we can make a judgment, and there is no need to perform an erase operation to write. The main point is that first of all, our users may store the code in the previous area, and then the latter area is used by flash to simulate EEPROM. Users may store data in sector behind flash, so when we write data of a sector, we can first read the sector into a RAM. Then we can modify the data you want to write in RAM. After modification, we write it back, This is a read, modify and write operation. In this way, we can ensure that the previously stored data will not be changed. How to implement it? For the read operation, we can actually perform a read operation like memory, and read is relatively simple. As for write, as we have just said, it is a read, modify and write operation. Then I will introduce some difficulties encountered when using Flash to simulate EEPROM on APM32F4 MCU. You can take a look, and this is a storage structure of APM32 Flash. It includes a main storage area and an information storage area. We only need to look at the main storage area. We can see that its start address is 0800000. The size of the first 4 sectors is 16K, and the size of the 4th sector is 64K. The size of the sectors from the 5th to the 11th is 128K. We can see that the sector size of the F4 series is large. The minimum is 16K and the maximum is 128K. As we mentioned earlier, to ensure that the data in Flash is not rewritten, we need to first create a buffer with the same size as the Flash sector and RAM, rewrite the data in the buffer, and then write it back into Flash. But for our Flash, if you want to take a sector size of 128K in Flash, you would want to create a RAM space of 128K, which is impossible and also a waste. A RAM space of APM32F4 is 192K. You can create such a large space, but you can use the remaining 64K, which may be small for applications and is also very wasteful. So we cannot use 128K or 64K sectors. We can select the sector with a size of 16K as a sector for Flash to simulate EEPROM. We can use the sectors 1 to 3 to implement simulation of EEPROM with Flash. So how can we use these 3 sectors to store your data? When the compiler is compiling data, it will generate a link code from 800000. These 3 sectors may be occupied by the code area. Therefore, we can first define a space with the same size as EEPROM to define the array of a const. And then you can specify this array to the start address of the sector you want to simulate. This compiler provides some extension keywords and can specify where the array you defined is stored. But it is important to note that the size of this array must be an integer multiple of the sector, which is because when we erase data, the entire sector will be erased. If you define 1.5 sectors, 2 sectors may be erased. If you use them, your code might be erased. So the defined size must be an integer multiple of the sector. Then we can open up another RAM buffer. As mentioned earlier, the size of this buffer can be the size of a sector. We rewrite the data of this buffer in RAM and then write it back to Flash. If we divide it in this way, the final Flash area is divided as follows. First, for number 0 sector, we must use it to store code, because the hardware of the sector needs to run the code from 800000 to power on, and we cannot occupy this sector. Then, the next sector is large, so it is not applicable. Finally, we select these 3 sectors to introduce Flash simulating EEPROM. You can choose only one sector, or choose all these 3 sectors. Next, I will introduce the implementation of the code for Flash simulating EEPROM. For the code, let's take a look at some macro definitions. These macro definitions are the 3 sectors, as we just mentioned, which are used for Flash simulating EEPROM, namely, sectors 1 to 3. You can use only one sector or all these 3 sectors. The size of this macro is 1 sector. This macro is the number of sectors you want to use to simulate EEPROM, namely the size of total Flash of the simulated EEPROM. The macro I define here is the size of 2 sectors, and it is a start address of Flash simulating EEPROM. This macro is an end address of Flash simulating EEPROM. An interface function is provided for users, and it is a read interface function. The first parameter is the address you will read. The second parameter is a pointer, which indicates where you want to store the data. And the third parameter is the read length. The write interface functions is the same. One is write address, and this is a write pointer. Next, let's take a look at the test code. We can select a specific address like Flash and write a certain data length. Here we can select an address, which is an end address close to the cross sector. For example, the address I chose is an end address close to sector 1. That is to say, we provide an interface function, as we can test whether we can read and write across sectors. The following 3 situations are tested. The first is write by byte, the second is non-byte aligned write, and the third is cross-sector write. We can see the picture of its memory data on the right. The first write is performed by aligning with the address. After performing the write operation, the first byte of the written data is 001 followed by 3A. The second is that we don't write by aligning with the address. We can see that the value of this address is added by 7. It is not aligned by 4 bytes, but it can also be written normally. Then, the writing of the third data is cross-sector read and write. We can see that it can also write data normally. We wrote 03, and then CCCCC. That is to say, the implementation and reads write of one of its codes is consistent with the experience of EEPROM. Next, I will explain another scheme of using Flash to simulate EEPROM for your reference. In this scheme, a storage format of its data is like this, and it must first use 2 sectors of the same size, i.e. Sector 0 or Sector 1. One sector can be in an effective state and is active, and is being read and written all the time. The other sector is in an erasure state, as we can see that all the data is FF. This sector is in a standby state at any time. As long as Sector 0 is full, the valid data of Sector 0 will be transferred to this sector. It has a formatted fraction for storage, in 4 bytes. The first 2 bytes are used to store data, and the latter 2 bytes are an address of storing this data, and it is called virtual address. Because it is not a real address, we just write the corresponding address of this data into Flash, and we address the data based on this virtual address. As for the size of the stored data, for example, if the size of our sector is 2K, the size of stored data is dividing 2K by 4. Because every 4 bytes are used as a reassembly unit, subtract 1, and obtain a 2K sector, and it can store up to 511 data. In this storage scheme, 1 sector or a state of page is, as mentioned earlier, 1 sector will be in an effective state, and this effective state actually contains all the valid data that you are currently reading or writing. The other sector is in an erasure state. It is an empty sector, and the data inside it is erased to FF. When the first sector is full, a valid data of the entire sector will be transferred to the erased sector. It is important to emphasize the valid data. The data in it might be written repeatedly, and some data may have been overwritten, but you do not really need it. Therefore, the valid data is actually the data you last wrote. We will move the valid data to a sector and the erased state. This is an update process of data. To write data, start addressing from the start address of the sector. Then find the first one data is erased, which is 0xFF here, and this position is erased. Then we can write a variable data you want to store from this position, and a virtual address corresponding to this variable. Reading data is the opposite, and it starts addressing from an end address of the page or sector. Address to the first, which is the last change data. We can see that the virtual address here is the same, which is your virtual address. if the data you want to store is changed. So you definitely want to save it. Then you will return the last valid data to you. So addressing is to find the last changed data. Return to the user. For transfer of data, when the sector 0 is already full and cannot continue to write data, we will move a valid data of the entire sector to an erased sector. It is emphasized again that the valid data is actually the last changed data. Take 0 times 0005 as an example. The virtual address is 7777, rather than this data. That's all for today. Thank you.